This video will cover how to set up the tank losses block that's new to ProMax version 6.0. For those of you who may have used previous versions of ProMax, this is similar to the 2019 tank losses stencil, but this new block is much faster and has some additional calculation options. Just like the stencil, this block follows AP42 calculation methodologies. ProMax can calculate storage tank emissions from various types of oil and water tanks, both fixed and floating roof configurations, as you see here, including internal, external, and domed external floating roof tanks. All of these are contained inside of the AP42 documentation, and we have calculations in ProMax for those as well. Let's take a look at the different types of storage tank losses we're going to be looking at. Again, these come typically from AP42, and we'll talk a little bit more about what each of them is and how we're calculating them. The first type is flashing. Flashing losses are instantaneous vaporization as the pressure drops down to atmospheric into our storage tanks. This says AP42 Chapter 7.1 honorable mention, just because AP42 does mention flashing losses, but only to say that that's outside the bounds of what the document covers, and it doesn't give any recommendations or requirements for how to calculate that. So for the flashing emissions, we use ProMax thermodynamic equations of state, whatever you select inside of your ProMax model. We use that equation of state and some binary interaction parameters that we have accumulated over the course of 45 years to figure out where those hydrocarbons actually want to go in what phase. And it's pretty robust and a very good method for determining what those flashing emissions are. We also have working and withdrawal losses. Working losses are for fixed roof tanks. That's when you have vapors pushed out of the tank as liquid fills that storage vessel. So essentially in a fixed roof tank, you have some amount of vapor space that sits above the liquid in that tank. And as you fill that tank with more liquid, some of that vapor is pushed out. That's what we call working losses. That comes from AP42 Chapter 7.1. We also have withdrawal losses. These are for floating roof tanks. As liquid is pumped out of our floating roof tank, some amount of liquid clings to the sides or the fittings of that vessel and evaporates, and that's what we call withdrawal losses. We also have breathing, or also known as standing emissions. Again, this comes from AP42 Chapter 7.1. The breathing or standing emissions happen as temperatures increase throughout the day. The temperature of the liquid sitting in that tank also increases, and some vaporization occurs because of that. So this is the liquid standing in the tank throughout the day, and it breathes or vaporizes some of the liquid as that temperature increases. We also have loading emissions. Those are vapors emitted from the tanker truck or the rail car, whatever loaded vessel, as liquid fills it. Those trucks or rail cars or vessels are not held at a vacuum. That would be rather expensive. So typically what actually happens is there's some amount of vapor sitting in that tanker truck or that rail car when it comes up to the well side, wherever it's being loaded. And that vapor will be displaced as we fill that vessel with liquid to then send it wherever it's going. So that is what our loading emissions are, those vapors that are emitted as we load that vessel that's taking our oil somewhere else. New in the tank losses block that was not previously available in the stencil are the short-term emissions. So we have short-term working and short-term loading emissions. Those come from TCEQ documentation. This is essentially looking at worst case short-term emissions during routine operations. Primarily that's going to be conditions at a worst case temperature of 95 degrees and the associated parameters like vapor pressure that are affected by those worst case conditions. And we'll take a look at some of those as we move on. No matter which type of emissions you're looking at, do know that we work very hard to make sure that you get good results from the simulation. This comes from a study that was done a few years back, a third-party study that was comparing data points that they took to various calculation methodologies. ProMax wasn't initially included in the study, but they did publish their data. So we plugged that data into ProMax to see where we fell. And as you can see from that chart, we were pretty happy with the way that turned out. So take that for what you will, but do know that we work very hard to make sure that if you put in good information to the simulator, you'll get very good, very accurate information that comes out. Okay, let's jump into the ProMax side and figure out how to specify our new tank losses block. So we'll come into our ProMax model. Again, this is version 6.0. The tank losses block will not be available in ProMax 5.0 or earlier versions, but in ProMax 6.0, you can go to the ProMax Auxiliary Objects shape set over on the left-hand side of your model and find the AP42, that tank losses shape. We'll click and drag that out. We can see that I've already got some streams attached over here on the right-hand side. So we have our pressurized liquid entering our atmospheric tank. This is coming from upstream, maybe at a well site. If you have a heater treater, it might be coming out of that heater treater or separation upstream. And then we're going to put it into this tank, and that tank has multiple outlets. We have some letters to help you out with what that means. The F is for flashing, those flashing emissions that we talked about. The W is for working, the S is for standing, L is for loading, and R is for residual. The residual liquid is what comes out after the flashing, working, and standing have happened in that tank. The loading stream is not required. You can do this block without a loading stream. If you are sending this all to pipeline and you don't actually load your oil into a tanker truck or a rail car, then you may not need that loading stream. If we take a look inside of our block, I'll double click on our AP42 block to get inside of it. We can see our process data tab is where most of the magic happens, just like usual in our ProMax blocks. In that process data tab, we'll look at the working and standing grouping on the left-hand side first. This is where most of our information is going to be specified. The very first option that we have is to set the tank geometry. These are those types of tanks that we looked at just a moment ago. We have vertical and horizontal cylinder, those are fixed roof tanks. And then we have the various types of floating roof tanks as well. I'll flip to one of those here in a little bit so we can see what difference that makes in the block. But for now, we'll keep that as a vertical cylinder. We do need to specify a shell length and a shell diameter. I'm going to say our shell length is 25 feet and our shell diameter is 12 feet. We need to tell it the number of storage tanks we are using in this case. I'm going to put 3 storage tanks. And when you put any number greater than 1, we assume that all of those storage tanks are operating the exact same way. So what we do is we take your inlet throughput, in this case, divide it 3 ways to these 3 different tanks. We do the calculation on a single tank because that's the way AP42 was written, was for a single tank. And then we multiply the results by however many tanks you had at the end, again, because we're assuming that these all work identically. We have a maximum, average, and minimum fraction fill of tank. If you have better numbers for your specific tank, please do feel free to put those in. We do need to set a material category as well. We have a drop-down option here for light organics or heavy crude. AP42 says that we should use one multiplication factor for light organics and a different one for heavy crude. It doesn't tell you specifically in AP42 which one is which, but the general rule of thumb that we know of is about 40 degrees API gravity is the cutoff point. I know in my example here, I have an API gravity, I think about 70, so we'll choose light organics as our material category. We also have insulation options. The options that you have are uninsulated, means that there is no insulation on that tank. Partially insulated, which means the shell of the tank is insulated, but the roof is not. And a fully insulated tank, which means the shell and the roof are both insulated. If you choose a fully insulated tank, you will have the option to set some information about a heated tank if that's what you have. AP42 says if you have a partially insulated tank, there are no other modifications that need to be made. If you have a fully insulated tank, there are some additional calculations or additional pieces of information we can input. For our purposes, I'll leave ours as uninsulated here. You can check if you have bolted or riveted construction or vapor balance tank. That will change some parameters inside of the equations. You can also check on a known sum of increases in liquid level. AP 42 says that you can set a sum of increases in liquid level to use instead of your whole throughput. If you have a tank that is being emptied and filled at the same time, you may have some lower emissions if you set the known sum of increases in liquid level, if that's a value that you know. Otherwise, we'll use our throughput from our inlet stream, and that's what I'm going to use in this case. I'll leave that checked off for now. We have some paint characteristics to set. I'll say my shell and roof color maybe are medium gray. And then we have our shell and roof paint condition. We have a few options there. New, average, and age. I'll leave mine at average. If you want some more information, those are all defined in AP 42, Chapter 7, if you're interested in looking at that. We can also choose our roof type. You can choose between cone or dome. If you have a cone type, you need to give us the slope of the coned roof. That 0.0625 is a default given by AP 42. If you don't know a better number, you can leave that default. If you do know what yours is specifically, feel free to overwrite that number. If you choose a roof type of dome, you'll need to give us the radius of the domed roof instead. That's grayed out here because we've chosen the cone roof type. We have the breather, vent, and vacuum pressure. Those are defaults given in AP 42. Typically, we don't need to change those unless you do know that you have something different, but I'll leave mine at the default for now. For the tank conditions, the first thing we need to set is the location. If you use the drop down, there's a big long list of different locations that are available. These are all from AP 42. That will set the meteorological conditions for this tank's operation. So I'm going to say mine is in Dallas. So I can type in Dallas and hit enter, and that'll take me to Dallas-Fort Worth. From here, we can see that the meteorological conditions have been filled out below. The average daily minimum maximum ambient temperature, the daily solar insolation, atmospheric pressure, wind speed, all of those things. If you don't find a location that is close enough to your site, you can go to the very top of that list and choose custom location. If you choose custom location and hit enter, then you'll see that we can now specify those meteorological conditions, and you can overwrite those to whatever is more appropriate for where your site is located. In my case, I'll keep it at Dallas, so I have all those pieces of information already filled out for me. The time frame that you can choose is either year or annual, or any one of the months of the year. If you choose one of those months, it will look at the meteorological conditions for that month and use those in the equations. I'll leave mine at year, so we'll look at just the annual calculations here. We have the known liquid bulk temperature that you can check on. If you check that on, you'll be able to set your own liquid bulk temperature. If you have a measured bulk temperature that you would like to use, feel free to do that this way. Otherwise, we'll use AP 42 calculations to come up with what that liquid bulk temperature is based on the other inputs that you've provided. There's also a checkbox for use AP 42 Raoult's vapor pressure. AP 42 does allow Raoult's law to be used to calculate vapor pressure, and you can check that on, and that's the method we'll use in that case. If you leave it checked off, like I have here, that will use ProMax thermodynamics to figure out what the vapor pressure is based on the equation of state that you've selected. And again, those binary interaction parameters, it's a bit more robust than Raoult's law. So that's why we have this as the default selection, but you can check it on if you'd like to use Raoult's law instead. If you have a water tank, do not use Raoult's law for vapor pressure. It does not apply to water tanks. Flashing temperature is a default that we calculate. We use the maximum liquid surface temperature based on the location selected as the default. But as we mentioned before, AP 42 doesn't give any requirements or recommendations on what that flashing temperature should be. So if you think you know a better number to use, feel free to do so. It does just need to be at least the bulk temperature of the liquid. We can't go below that for the flashing temperature because the flash does happen first. Down towards the bottom, we have those heated tank conditions. Again, if you have a fully insulated tank, you can then have the option to specify some information about the heated tank. The additional calculations at the bottom, I'll come back to here in just a little bit. That's where we have those short-term emissions that we talked about earlier. And again, I'll come back to that in just a second. We'll get through the regular groups first before we talk about that new feature. So far, we've been playing in the working and standing grouping on the left-hand side in our project viewer here. Below that working and standing grouping is the loading grouping. And this will only appear if you have a loading stream attached to your block. I mentioned that loading stream is optional. So if you do not have a loading stream attached, this loading section will not appear. If you do have a loading stream attached like I do here, that's why we have options to specify information about the loading. We need to choose a cargo carrier in a land-based mode of operation. I'll say we've got maybe a tank truck, and we've got submerged loading of dedicated normal service. That's what I will choose here. Below that, we have a few options to calculate efficiency. The overall reduction efficiency is the combination of the control efficiency and that truck annual leak test passed. So if you know your overall efficiency, you can set that. That's what we had previously in the tank losses stencil in previous versions of ProMax. We've added now that you can set the control efficiency and which leak test, if any, your truck has passed instead. So if I say we've got a super sophisticated system here, maybe a control efficiency of 98%, we're sending all of the loading vapors to flare, and we know that our truck has passed the highest level leak test, MACT level, we can see that it calculates for us what that overall reduction efficiency is based on those two things. If you didn't have any extra control devices, if your truck had not passed a leak test, your overall reduction efficiency would typically be 0% in that case. Okay, from here, go back to our groupings on the left-hand side. I'm looking at the loading grouping. Below the loading grouping is the results grouping. And from that results grouping, we can see some information about what is calculated after we execute the block. So I can execute the block with the execute button up at the top, or I can hit execute flowsheet from up at the top, execute project. Either of those will work. In this case, we can then see the calculated values for our flashing, the combination of working and standing, and then the breakout of working and standing individually, and loading losses. We have the total emissions and also the emissions per tank. Remember, we have 3 tanks in use in this case, so that's why those numbers are a little different between those 2 columns. You can also choose what subset you would like to look at. By default, we're looking at just the VOCs, so typically that's C3+ with a few other exemptions. If you wanted to see all of your components, you can choose all selected, and that will give you the values for all of your components, including methane and ethane or any of those non-VOC components. So you can flip between those and choose what summations you'd like to see. We've been looking so far at the results grouping at the summary tab. That's where we see those basic pieces of information. We also have these detail tabs, so working details, standing details, and loading details. These are the variables that are pulled for AP42 equations. So if you're curious how we came up with the numbers in that summary, you can take a look at these details pages to look at those different variables that are used within those AP42 equations. Do be aware that if you're looking at the AP42 equations, you want to be looking at the component subset of all selected because the VOC summation is done after the calculations occur. In this case, I'll keep looking at that VOC's subset. Okay, so that's for fixed roof tanks. I'll come back to my working and standing grouping, and as promised, I'll flip this over to a different tank geometry. I'll choose an external floating roof tank. Whenever you select a different tank geometry, the options that you have to specify within this table will change. So if I choose the external floating roof tank, we notice that the options in that table change a little bit. We have an external floating roof type of pontoon or double deck to choose from. I'll keep mine at pontoon, but some of those options no longer appear because they don't apply to floating roof tanks. For floating roof tanks in particular, we also have a new grouping that pops up. So underneath the working and standing grouping, we have the floating roof grouping. That will take us to the different types of fittings that are present in our particular floating roof. We do have default options set for when AP42 says that these are defaults that can be used. There are a couple that AP42 does not have default values for. That's this unslotted and slotted guide pull type. So you do have to set those yourself because AP42 says that there are no defaults that are applicable over a broad range of tanks. Those are very specific to each particular tank. So I'll say NA for both of those. I'll say we don't have those in this case. Please feel free to overwrite any of those other options if you have better numbers. Again, these are just the defaults that are provided by AP42 based on the other specifications that you've made. If we take a look back at our results grouping on the left-hand side now and re-execute, we can see we have a few more options here. We have rim seal and deck fitting losses. Sometimes you'll also have deck seam losses, depending on the type of floating roof you've selected. All of those are grouped together here. That is also the same as standing losses, as the summation of those different types of losses, but we break them out for you for the floating roof type. Similarly, we have these details tabs. Those are slightly different than what we saw in the fixed roof options because we have different equations for the floating roof fittings and all of the emissions that go along with those. So you see a little bit different table here in the standing details in particular, but that just has all of the information that we're using to calculate those AP42 emissions for floating roof tanks. I'll take a look back at my working and standing grouping so I can come to this additional calculations section. I'll check on that include short-term emissions checkbox, and as soon as we do that, you see on the left-hand side there's a new grouping that appears called short-term. If I click on that short-term grouping, I'll have the option to specify some information about those short-term emissions. We do need a maximum battery pumping rate. These are pieces of information we need for the floating roof tank. That's what we're still looking at. So that maximum battery pumping rate, I'll say, is maybe 100 barrels per hour. In this case, I'll say maybe I just want to look at a single tank instead of all 3 tanks in the battery. I'm just going to look at one tank for a worst case scenario for that one tank. For floating roof tanks, you have the option to use the worst case month or the worst case wind speed. If you leave those checked on, we'll go through all of the months for your location and figure out which one gives the highest emissions and use that. If you want to set your own values, you're more than welcome to do so. Just uncheck those used worst month options and you can set your own values there instead. For loading conditions, I'll again say maybe we have 100 barrels per hour. And in a worst case scenario, I'm going to say we have 0 reduction efficiency so that we get no reduction in emissions based on other pieces that we have attached. So just kind of a worst case option there. From here, we can look at the results. Notice the results tab for short-term emissions is to the right of the specifications tab in that short-term grouping. So I can execute the block. We can see that the worst case liquid surface temperature and the worst case wind speed have now been calculated based on the month that gave the highest emissions. And if I take a look at the results tab, I can see what those emissions are. We get that in pounds per hour. And again, we have that breakdown of the different types of losses that you might be interested in seeing. You can also look at the details tab, which gives you more information about the pieces of information we're using in those equations. One of those being that worst case month, which month returned the highest emissions. In this case, that is July. That's for floating roof tanks. If I come back to my working and standing grouping and switch back to my fixed roof option, my vertical cylinder fixed roof, notice it did save everything that I had previously saved, so I don't have to go and put in any of that information again. If I come back and look at the short-term grouping, I see in the specifications slightly different information because we have, again, different equations for fixed roof and floating roof tanks. So I need to give it a maximum battery filling rate. I'll again just use 100 barrels per hour here. I'll again just use one storage tank for the worst case. And then we have the option to set the worst case liquid surface temperature. TCEQ recommends that that be typically 95 degrees or the actual temperature, whichever is worse. So in this case, I'll leave that at 95 degrees Fahrenheit. I can execute, again, take a look at that results tab, and we can see in this case we don't have all of the additional breakout for the rim seal losses and the deck seam losses. We don't have those for fixed roof tanks, so it's a little bit shorter list, but we do have the worst case flashing losses in addition to the short-term working and loading losses. Just like last time, we do have that details tab as well, where you can see information about what variables are that we're using to calculate these. One more thing to show you before we finish up here. I'll close out of Project Viewer and come back to my flow sheet. I'll show you how to display some information on your flow sheet from that block. So if we come to our ProMax shape set over on the left-hand side, I can find the ProMax Streams shape set and pull out a property table. We'll click and drag that out onto our flow sheet, double click to get inside of it, and then we can specify what information we want to display here. In this case, we're looking at the flow sheet called AP42 bulk temperature. The grid column, I'm going to call the block, the tank losses block called tank 100. And in the grid rows, I want a property of that tank losses type block. The information I want is in the results grouping. Remember those groupings we were looking at inside the block. Then we can grab the flashing, working, standing, and loading losses from here. I want all of those in tons per year. That's typically what we care about. So I'll change my units for all of those to tons per year, and I'll increase the font size just a little bit so we can see it a little better on the screen. So I'll choose a font size of 10, click OK, and now we can see that that information is displayed on the flow sheet. This is based on the component subset that you selected within the block. So right now we're looking at the VOC emissions. If you change the type of components you're looking at in the block, that'll update on the table here as well. You can also grab information from any of the outlet streams, use a call out like we have here. If you want to sum up those pieces of information, you can call them out from the streams as well as the block like I've shown here. And that is the basics of our new tank losses block. If you have any questions as you start working with this or curious about anything, please feel free to give us a call or shoot us an email at support@vre.com, and we'll be more than happy to help you.